Light should not be able to cross emptiness. A lamp turns on and the wall appears. The sun rises and the world becomes visible. A star burns in a distant galaxy, and after traveling for millions of years, its light enters a human eye. We call this simple. We say light travels. But if Albert Einstein had accepted that word without questioning it, modern physics would look nothing like it does today. Because the moment you ask what is actually traveling, the familiar world begins to lose its shape. Is light a wave moving through space? Is it a stream of particles flying from a source to a detector? Is it a disturbance in fields that have no material substance? Or is travel only the closest word we have for a process that does not fit ordinary human imagination? Einstein's life in physics can be read as a lifelong argument with light. Light challenged his childhood intuition. Light helped him destroy the old separation between space and time. Light led him to the photon, one of the foundations of quantum theory. And then light helped create the very quantum mystery he could never fully accept. The story begins with an idea that once seemed completely reasonable. In everyday life, waves need something to wave in. Sound travels through air. Ocean waves travel through water. A vibration travels through a string. So when 19th century physicists concluded that light behaved like a wave, they naturally asked what medium carried it. They imagined space filled with an invisible substance called the ether, weightless, transparent, everywhere, the hidden ocean through which light rippled. Then came the failure. If Earth moved through this ether while orbiting the sun, light should have behaved differently in different directions, like a boat moving with or against a current. Albert Michelson and Edward Morley built a delicate instrument to search for that difference. They expected to detect the ether wind. They found no convincing trace of it, no preferred direction, no hidden current. No sign of the ocean that light was supposed to need. The ether did not simply vanish overnight from everyone's mind, but its old role was wounded. Light still behaved like a wave, yet the medium had slipped away. Something was oscillating through empty space, but it was not air, water, or any ordinary material. Maxwell had already supplied the next clue. His equation showed that electricity and magnetism were not separate phenomena. A changing electric field can produce a magnetic field. A changing magnetic field can produce an electric field. Together, they can sustain a traveling electromagnetic disturbance. That disturbance is light. Nothing material has to flow from the bulb to the wall. Electric and magnetic fields change together, and their changing pattern moves through the vacuum. Maxwell's equations even predicted the speed of this disturbance, about 300,000 kilometers per second. The speed matched the known speed of light. It was one of the most beautiful unifications in science, but it left a dangerous question behind. If there was no ether, what was this speed relative to? This is where Einstein's question became revolutionary. As a young man, he imagined what it would be like to chase a beam of light. If you could run beside an ordinary wave, you might see it frozen, a standing ripple beside you. But Maxwell's equations did not seem to allow a frozen light wave. Light, in the equations, always moved at the same speed. Einstein took that clue seriously. In 1905, he proposed that the speed of light in vacuum is the same for every observer moving at constant velocity. This sounds harmless until you compare it with everyday motion. If someone throws a ball toward you while you drive toward it, the ball approaches faster. If you drive away, it approaches more slowly. Speeds add and subtract. That is the world of Galileo and Newton. Light refuses. Move toward a beam of light, and you still measure the same speed. Move away from it, and you still measure the same speed. The universe does not adjust light to fit your motion. Instead, Einstein realized space and time adjust. That was the price. If light's speed is fixed for everyone, then distance and duration cannot be absolute. Moving clocks tick differently. Moving lengths contract along the direction of motion. Events that one observer calls simultaneous may not be simultaneous for another. These are not optical illusions or measurement mistakes. They are the structure of spacetime. Light had forced Einstein to abandon the old stage of reality. Space was not a fixed arena. Time was not a universal clock. They were woven together, and light followed the null structure of that space-time, the paths that define the absolute limit of cause and effect. This was not only a philosophical change. Fast particles in accelerators live longer than they would if time were absolute. Muons created high in the atmosphere survive long enough to reach the ground because from our frame, their internal clocks run slow. GPS satellites must correct for relativistic time effects or their positions drift. Light had not merely changed Einstein's equations. It had changed the technology that now guides aircraft, phones, ships, and the clocks above our heads. The simple question, how does light travel, had already changed the meaning of travel. But in that same year, Einstein opened a second door, and this one led into stranger territory. The problem was the photoelectric effect. When light shines on certain metals, electrons can be knocked out of the surface. If light were only a smooth classical wave, brighter light should always deliver more energy. Given enough brightness, even red light should eventually push electrons free. But experiments did not obey that expectation. Below a certain frequency, red light ejects no electrons no matter how bright it becomes. Above that frequency, even dim blue or ultraviolet light can eject electrons. Brightness changes the number of electrons released. Frequency determines whether the release can happen at all. Einstein's explanation was bold. Light transfers energy in packets. Each packet carries an energy proportional to its frequency. More brightness means more packets, not more energy in each packet. If a packet does not have enough energy, it cannot release an electron. If it does, one packet can release one electron. Those packets are what we now call photons. Einstein had helped reveal that light was not just a wave spreading through fields. It also arrived in indivisible exchanges of energy. A detector does not always receive light as a perfectly smooth stream. At low intensities, it records separate events. A click, then another, then another. Light spreads like a wave, but it is detected like a particle. And the more carefully scientists looked, the less willing light became to choose one ordinary identity. Take the double-slit experiment. Send light through two narrow openings, and a wave-like interference pattern appears on the screen. Bands of brightness and darkness, the signature of overlapping waves. Now reduce the light until photons arrive one at a time. Each photon lands as one localized dot. Yet after many photons, the same interference pattern slowly builds up, one event at a time. A wave pattern from particles that arrive individually, then place detectors at the slits to learn which path each photon takes. The interference disappears. The pattern becomes more particle-like. The result depends not on human curiosity, but on the physical information made available by the experimental arrangement. When which path information exists, the alternatives no longer interfere in the same way. This was the kind of result Einstein found impossible to ignore and difficult to accept. He had helped create the photon concept, but the theory growing around it seemed to replace definite stories with probabilities. Quantum mechanics did not always say, here is the exact path the photon took. It said, here are the probabilities for what may be detected. Einstein accepted the success of the calculations. He did not deny that quantum mechanics worked. Its predictions for light and matter became extraordinarily precise. What he questioned was whether the theory was complete. Were probabilities truly fundamental, or did they hide a deeper layer of reality, something not yet discovered? This was not stubbornness against evidence. It was a struggle over what physics should mean. Einstein had already taught the world that intuition could be wrong. He had changed time itself. But he still believed physics should describe an objective reality existing independently of observation. He wanted the moon to be there whether anyone looked at it, and he wanted the properties of physical systems to have a deeper, definite reality, even if we did not yet know how to describe it. Quantum experiments with light pressed against that hope. In the standard textbook interpretation, quantum mechanics does not assign one definite classical history to a photon before measurement. Other interpretations describe the underlying reality differently, and physicists still debate what the theory means. But all successful interpretations must reproduce the same experimental facts: interference when alternatives remain indistinguishable, definite detections when light interacts with measuring devices, and probabilities that are not just ordinary ignorance in the classical sense. Einstein's discomfort reached its sharpest form when quantum theory suggested connections between distant particles stronger than classical intuition allowed. In 1935, with Boris Podolsky and Nathan Rosen, he argued that quantum mechanics seemed incomplete if it allowed such strange correlations between separated systems. But decades after Einstein raised the objection, physicists discovered a way to turn his philosophical concern into an experiment. Later experiments inspired by Bell's theorem showed that no theory based only on local pre-existing instructions could reproduce all the correlations seen in quantum experiments. These tests did not settle every interpretation of quantum mechanics, but they strongly challenged Einstein's preferred hope for a simple local reality beneath quantum predictions. And light has often been one of the tools used to reveal that challenge. Photons can be entangled, meaning their measured properties are linked in ways that cannot be explained by ordinary pre-written instructions while preserving locality. Measure one photon here, and the statistics of its distant partner show correlations stronger than classical physics permits. This does not let us send messages faster than light. Einstein's speed limit survives. But it does show that reality is not built from the comfortable, separable picture he wanted. This is the remarkable arc of Einstein's relationship with light. First, light forced him to change space and time. Then light helped him create the photon. Then photons helped build the quantum theory that challenged his deepest instincts about reality. He won one revolution and resisted another, and modern physics carries both parts of his legacy. So what, finally, is traveling when light travels? At one level, an electromagnetic disturbance propagates through space. Electric and magnetic fields change together. Energy and momentum move from a source to a detector. In vacuum, this propagation occurs at the invariant speed c, the speed limit for cause and effect. At another level, light is quantized. It is exchanged as photons, discrete quanta of the electromagnetic field. A photon has energy, frequency, momentum, and no rest mass. It can be emitted by an atom, absorbed by a detector, and counted as a single event. But the deepest picture is not a tiny glowing bead flying through space like a bullet. Quantum theory does not always give us a simple movie between emission and detection. It gives us a mathematical structure that predicts possible outcomes and their probabilities with extraordinary accuracy. That answer can feel unsatisfying because it does not match the images our minds prefer. We want a wave or a particle, a path or no path, a thing here, then there. But light lives at the point where those classical categories fail. Even time behaves strangely at that boundary. A photon has no valid rest frame. You cannot ride beside a photon and see the universe from its point of view. Special relativity does not allow an observer to move at the speed of light. So when people say no time passes for a photon, they are using a shortcut. The careful statement is that light follows a null path through spacetime, and the proper time along that path is 0. For us, sunlight takes about 8 minutes to reach Earth. For the photon, there is no ordinary clock traveling with it that can measure a journey. The language bends because it was built for slow objects with mass, not massless quanta, moving along the boundary of causality. And yet this difficult thing is what makes the visible universe possible. Every color you see is connected to photon frequency. Every shadow marks where photons were blocked. Every reflection is light interacting with matter. Every photograph is a record of photons arriving and being absorbed. When you look at the moon, photons that bounced from its surface enter your eyes. When you look at a distant galaxy, Photons that began traveling before human civilization finally end their path in a telescope. The universe is visible because light can cross emptiness. But light itself refuses to become a simple image. That is the irony Einstein lived with. The thing that reveals the world also reveals the limits of our ordinary thinking. It showed him that time is not universal. It showed him that energy comes in packets. It showed him that the act of measurement cannot always be treated as a passive glance at a fully classical story. And it left him asking whether quantum theory was the final truth, or only a powerful map of something deeper. Modern physics has not returned to the comfortable world Einstein hoped to preserve. Experiments have supported relativity again and again. Quantum theory has become one of the most successful frameworks in science, and the dream of a simple classical picture underneath has become much harder to defend. But Einstein's questions did not fail. They became sharper. They forced physicists to ask what a theory is supposed to describe. They forced experiments that tested the foundations of reality. They left us with a universe more precise than imagination and stranger than philosophy. Return now to the lamp at the beginning. You turn it on and the wall appears. It feels instant, ordinary, almost beneath attention. But beneath that simple act, electromagnetic fields change. Atoms exchange energy. Photons are emitted and absorbed. Quantum probabilities become definite detections. Space-time sets the speed limit. Your brain turns those events into a world. Light is not simple. It only feels simple because it has been teaching your eyes since the day you were born. Einstein did not solve every mystery of light, but he showed that the familiar world was not the final world. He followed light until space and time changed. He followed light until energy became quantum. And when light led him into probability, he refused to stop asking whether reality had a deeper story. Perhaps that is the real mystery, not whether light travels, but what traveling means when the traveler has no medium, no rest frame, and no single classical path. Light is where fields, quanta, probability, and space-time meet. It reveals the universe while refusing to reveal a simple image of itself. What feels more mysterious to you, that Einstein used light to change space and time, or that light later challenged Einstein's own idea of reality? Subscribe to explore more documentaries through Einstein's questions, the questions that still guide us toward the deepest structure of the universe.